Hi, my name is Emmanuel Sachs. I'm in mechanical engineering, and I'm going to be leading up to introducing the idea of guided discovery in engineering science. So I've had the opportunity in my career to go back and forth between academia and industry. And probably the most powerful observation that I made most recently, I spent 7 years as CTO of a startup, is concerns the fact that individuals, engineers, are quickly pigeonholed as either analysts or they would call themselves designers, synthesizers. And you can see this even if you interview kids right out of a bachelor's program. They already have an idea about what they're going to be good at. And you can see how that becomes self-reinforcing because a manager wants to use their people most effectively. And so they'll say, okay, join this multifunctional team and you're the analyst. And of course, that's a relief to the person who thinks of themselves as an analyst because they don't have confidence in themselves as a designer. And that leads, in my observation, to projects going off the rails in some very predictable ways. And they often have to do with time. And so the designer will be busy plunging into perhaps the first concept that they came up with because the designer is not so good at doing the first order analysis. Meanwhile, the analyst is maybe a little bored by the first order analysis, and they're trying to get ready for the third order analysis, which will certainly be critical to the success of the technology in a few months. But really what the designer needs to hear is that this is really not a good idea. You should go back and come up with something else. But what I also note, and I think we all know this, that the best engineers can do both analysis and synthesis, and they know when to switch from one mode of thinking to the other. And in my view, our primary goal as educators should be to get our students on a path that they can grow into becoming great engineers who can do synthesis and analysis and know how to move back and forth between them. So I call it the artful interplay of synthesis and analysis. You can do analysis artfully, you can do synthesis certainly artfully. But all you have in the interplay is art. There is no science there yet. So my argument is that this is the core of what we should be teaching, and furthermore, that this is the core of any human creative activity, and that makes it all the more powerful that we should teach it. But what makes it engineering, then? Well, you'll notice math and science don't appear yet. And so I put math agents, science agents, and something I called resource agents outside. So this artful interplay of synthesis and analysis is taking place swimming in a sea of agents of technology, those three types, science, math, and resource agents. So the science agents and the math agents are the things that we're all familiar with, and those are the things that we cover in most of our curriculum, it turns out, as you know, is spent covering those. Resource agent means anything that's been engineered before. So this could be a part I buy out of the McMaster car catalog. It could be a snippet of code that I download from the web. It could be a whole machine that becomes a subsystem in the larger system that I am designing. And the question then is, what does this say about how to change pedagogy? And I'd like to talk about two, and you see there are some there that are grayed out. The two that I'd like to talk about are that normally we teach math and science so that we can use them in analysis. But they are vital in synthesis, and we need to teach them so that students can use them in synthesis. And you think about science very differently when you're synthesizing with it. Abstraction and modeling should be more heavily emphasized, especially estimation and first-order modeling. So, because those are intimately tied with how you use science agents for synthesis. So what I mean by guided discovery is that the goal is to have the students discover the physical principles. And the reason for that is so that they create their own knowledge scaffold and hopefully remember it. Hopefully, those scientific principles then become ingrained in them. They become second nature. And then you can use them in synthesis. If they're not at that level, you can't use them in synthesis. You can only use them in analysis. So the target are concepts which seem difficult to communicate by other mechanisms, by all the things that we normally do. And the ideal preparation of the students is none at all. So I don't want the students to have had a lecture or watched a video on this, or to have read anything, or to know anything. I want them to discover it, as I tell them, as if they are the first human beings to be creating this piece of human knowledge. The students work in pairs, and each pair of students gets a piece of hardware. And there are challenges. So a challenge runs like this. The handout will say, in a moment, you're going to pull, push, twist, whatever, until this dimension becomes longer by this much, something like that. But before you do that, predict what you think is going to happen. So make your prediction and write it down, but also write down your reasoning, which is to say your model. Then go ahead and pull, push, twist, whatever, and make observations and measurements, and compare them to your predictions, and reconcile any discrepancies. So that's, of course, the key. So ideally, I think, between a third and half the time, there will be meaningful discrepancies, which is to say that the student's model was wrong. So probably not all the time, because that's probably frustrating. And if it's too infrequent, it's probably boring. So there's some sort of optimal there. But that creates the cognitive dissonance that wakes people up and causes them to create a new model. And that leads to long-term memory. So, the discrepancy might, an obvious answer, and you get this a fair amount, is, well, there's measurement error. Or, it's not really that different, it's close enough. And so then you have opportunities to talk with the students, one-on-two. Well, what do you think the measurement error is? And, well, what makes you say that's close enough? What would be not close enough? But then you get to the heart of the matter, which is to rethink the model. And that's where the gold is. And finally, the challenge is finished with a group discussion where you try and bring it together. And then you repeat with a new challenge. So that's the idea. Happy to take any questions.